Hello and welcome to the Toys in Space investigation. My name is Scott Anderson and I work here at the NASA Marshall Space Flight Center. In today's lesson, we are going to look at some toys that went to space. We are going to learn a little bit about the science of microgravity, and we are going to learn and have you practice what it's like to be a scientist or an engineer. The basic concept for the module is NASA sent some toys to space, and what we would like for the students to do is to play the role of the engineer and the scientist so that they will come up with predictions about what they think will happen when we try these toys in the microgravity environment of the International Space Station, and then to engineer possible solutions on how we might be able to make those toys work better. However, before we begin, I would like to tell you a little bit about some of the various NASA locations from around the country. Of course, I mentioned I'm at the NASA Marshall Space Flight Center, and we're located in Huntsville, Alabama. I will kind of wrap up with what we do here after I talk a little bit about some of the other NASA centers. And so let's begin down in the southeast. We have the Kennedy Space Center. If you know one thing about the Kennedy Space Center, you probably know that that's where we launch our rockets from. Not all of our rockets, but our space shuttle and our Saturn V rockets from the past launch there, and our new vehicle that we will use, the Space Launch System, to go further into deeper space, will be launched from the Kennedy Space Flight Center. Also, out on the West Coast, let's see here, let's go out to, let's say, the Jet Propulsion Laboratory, or JPL, as we sometimes call it. JPL, again, they do a lot of different things there, but if you know one thing about them, you know JPL as the home of the rovers. That's where we design and manage a lot of our projects, which would include rovers and satellites and landers. So that's what they're known for. And let's see, let's do one more before we come back to Marshall, the Johnson Space Center in Houston, Texas. Well, that is probably best known as the home for the astronauts. If you become a NASA astronaut, you will live and work somewhere around Houston, Texas. And when you report to your local center, it would be the Johnson Space Center. Okay, back to Huntsville, Alabama, and the Marshall Space Flight Center. If you know just one thing about the Marshall Space Flight Center, you probably know it's where we design and build rockets, including the model, as I have here, of the Saturn V, which is the only vehicle in the history of the world to bring humans to the moon. So it's rather important, and we also manage the Space Shuttle program, and we are working on a project now called the Space Launch System, which will bring astronauts further into space beyond low Earth orbit and possibly visiting Mars or an asteroid one day. But another thing we do, in addition to building rockets here at the Marshall Space Flight Center, is we manage payloads. We have a place called the POIC, or the Payload Operations and Integration Center. If you have ever heard of mission control, maybe from a movie, or maybe you know a little bit about how NASA operates, we have a place called mission control where the team on the Earth manage everything that happens with our astronauts in space. So one thing that happens when they have their work day and they begin and they're in space is many days they have to work on experiments. And these experiments are managed through the POIC so that all of the communication comes through here. And it's just like mission control for science experiments. Today, the students are going to be involved with playing the role of a scientist and an engineer. But I also wanted to introduce them to another career that we have here at NASA, and that works in the POIC, and that is the title of a lead increment scientist. Every time we have a group of experiments that are to be conducted from the space station, we will group them into what we would call an increment. And this is a period in time or part of a mission or connected with a launch where a group of experiments will be managed by one person. And you probably have figured that out. That is the lead increment scientist. And so we happen to have the luxury of having one of the lead increment scientists visit our studio here, and we wanted to ask them some questions. But the one that I'm going to play for you is their response to the question where we asked them basically, why are we exploring space at the space station, and how is this going to help us? And so here is an overview of why we are doing experiments at the International Space Station.
One of the reasons that we do research in space is because the environment on Earth is totally different from the environment in space. For example, on Earth we have that invisible force that we really don't see because we get kind of used to it, called gravity. So if you're going to live or colonize the moon or Mars, we need to understand the impact on us because we're not used to a very small gravity. So when we go out there, we have to do research to understand how things are going to behave. That's why that we use the ISS as a platform to do that kind of research as a test bed before we go and explore the moon and Mars.
So there, Dr. Jules was talking about some relevant things that we'll carry on with in a moment. He had mentioned that microgravity is something that we're going to have to learn to live in if we want to travel to Mars one day. But he also kind of talked about the space station as being a place where we can kind of learn things before we go on a more complicated mission, like to Mars or beyond low Earth orbit. And so while we're there, we're learning how to live in space. We're learning how to conduct science experiments so that we can use this knowledge on future missions that will go further into space. Some little tidbits about the science in space. The science on the ISS helps NASA learn, like we just said, about how we might be able to survive further into space. But another thing that a lot of the experiments and also just the process of living in space, a lot of these things come back to help us on Earth. At NASA, we call these things spin-offs, and what they are is basically technologies that may have been developed to help us live in space or travel to space, but they also have a practical use here on the Earth. And so some examples, you might even be familiar with this one, is maybe on television you've seen the commercial where the person is on a NASA-approved foam bed. What that means is that they've taken some of the technology that we use in our seats for our spaceships and applied it to a foam-fitting bed for you. And that's one example of a spin-off, but there are many, many more, including medical ones and other ones that you may not even think of, like the foam in your running shoes and how that helps you feel more comfortable. But the toys themselves, we put this experiment together as a way to engage students in having an interest in science and engineering. We realize that when we travel to Mars, or when we go there, it's going to be a long ways off. And so the scientists and engineers who are going to be supporting this mission probably are in a classroom today. So we want to generate this interest in what we would call the STEM career fields. And STEM is an acronym that stands for science, technology, engineering, and mathematics. And this is because these are some of the areas where NASA will be looking for employees as we partake in these missions in the future. So we're trying to get you interested in these topics so that maybe you'll pursue it as an education interest through middle school and high school and on through university. And so Toys in Space we thought would be a fun way to do that. And I think you'll enjoy that. Watching these toys and watching these lessons is going to, at least you'll have fun doing it, and that's probably one of the things we wanted to accomplish today. So on to the first topic, or probably one of the more important topics, and that's the science of microgravity. Perhaps you've seen an astronaut on television, or you've seen them in space, and they're floating around, and everything around them's floating, and the question is why? So now would be a good time for you to go ahead and pause the video and take a few minutes to talk about why things float inside the space station. Well, hopefully you've had enough time to discuss why things seem to float at the International Space Station. I will tell you, as someone who has talked to students from around the world several hundred times each year about this topic, you probably heard some wrong answers and maybe some right answers, just like I do. One of the biggest misconceptions with why things look like they float is the answer, there is no gravity there. And I will tell you, just first and foremost, that's not correct. There is gravity at the space station, but I guess by the same sense, it feels like there is no gravity. And so really what we want to know is, why does it feel like there's no gravity? And so I have this short descriptive method to explain why things float in space. Okay, so let's start with these three basic facts, and this is why things look like they float. Gravity pulls things down. Everyone knows that. NASA uses math to put things into orbit, and objects fall at the same rate. So let's go through these, and then we'll hopefully have everyone with a thorough understanding of why things appear to be floating, or as we would say, experience microgravity. Okay. I have a baseball in my hand, and everyone who's watching this knows exactly what's going to happen. When I throw this ball up, gravity is going to pull it down. So gravity pulls it down, and this would be true whether it's this remote or this mission patch. Anything I throw up is going to come down due to gravity. And so the scientists at NASA know this. And so part two is, well, we put things into orbit. So here's what happens, and let me do my best to demonstrate this with these active props. Okay, so this is the Earth, and we know things are pulled towards the Earth. So we have gravity pulling them to the Earth. So when we launch our rocket up, let's do it this way, even though this isn't the best example here. When we launch our rocket up, we know gravity will pull it down. So what the scientists do is they project the rocket to a certain location at an angle. So when gravity pulls it down and the engines stop pushing it away from the Earth, it falls down, but as it's falling down, it's missing the Earth. And it just keeps falling around the Earth and around the Earth. And you and I, we would call this orbiting the Earth. And so we have objects that are put into orbit, and they're released at a place where they're traveling around the Earth and falling around, just like our space station is. And so in this example of why things appear to be floating, we've got one more thing to cover, and that comes to us from before there was a NASA. This goes all the way back to Galileo. Galileo dropped stuff, you may recognize this as the Leaning Tower of Pisa. Back in 1589, Galileo conducted an experiment where he dropped two balls from the Leaning Tower of Pisa, and his observation proved that objects fall to the Earth at the same rate, regardless of how heavy they are. So if we had, I use two bowling balls because everyone usually knows that bowling balls have different weights, even though they're the same size and shape. So here we go. This is what happens. We drop a heavy bowling ball and a light bowling ball, and they fall together. So Galileo observed this. Okay. Pretend for a moment that I am in the space station. This is the space station, and we're orbiting around the Earth or falling around the Earth, and I have this orange here. Okay, let's say I have this, and I were to let go of it. What will happen when I let go? Well, again, as someone who's spoken with students all year long from around the world, I know there are going to be two answers, and they're both kind of correct. The first answer is someone says it will fall. And I guess technically they're correct because it's going to fall. However, you have to remember that the floor is also falling and I'm falling. In fact, we're all falling together. So although it's falling, it looks like it's floating, right? So again, think of me at the space station. We're falling around the Earth and I let go of it. It's going to fall too because Galileo taught us objects fall at the same rate. Now, for the record, I do want you to know that this is a demonstration. It's not really falling. It's an orange that's on a string. You just can't see the string so well. So that's why things look like they're floating at the space station. So there's just one more thing to talk about before we move forward, And it's just a demonstration of one of our astronauts talking about Newton's laws of motion. Hopefully this is something that you discussed in your class or maybe you've heard of before. But basically, Sir Isaac Newton, scientist, another well-known scientist, wrote some rules about how things move. And these are referred to as Newton's laws of motion. And they hold up in microgravity as well. But we have an interesting demonstration, and so I will play this video, and then we'll move on to the toy experiment. So here is Clay Anderson demonstrating Newton's laws of motion.
One of the things we have to talk about is Newton's laws. Anything in space, if we leave it just where it is, it will stay there unless it's acted upon by another force. So that football, theoretically, in 0G will stay there forever until somebody acts on it with a force, in which case it will move. And now, as that football goes, it will continue to move that direction until we stop it or give it a force in another direction. So think about that. If you were the field goal kicker on your football team, then you could do this. You could tee up the football, and all by yourself, you could kick that field goal right there. It's good!
So I hope you enjoyed that video. It's always fun to see that. It's just kind of neat to see the demonstration of how the football moves around and how it stays there. We are going to begin our toy investigation now that you will participate in. And for each toy, what I would like for you to do as the instructor is to pause at the moments where I ask you to and have a discussion with the students about how the toy might work. And then after we watch the video, maybe you could stop the video again here and ask them about how we might make it work better if it's something that's relevant. So for each toy, we'll let you have time to discuss it, and then you discuss it after the video as well. And then I will go through some of the popular ideas that I've heard on improving the toys over the years. And we are going to begin with a toy that most of you are familiar with. This is the jump rope. And I'm sure most of you are familiar with the basics of how a jump rope works. So let me have you pause the video now and discuss amongst yourselves some things. Like, we want to know, how does the jump rope work on Earth? What do you think will happen in microgravity? And then we'll watch the video and see what happens. And then after the video is done, pause it again and go ahead and discuss how you might be able to improve the toy of the jump rope.
Jump rope.
On Earth, jumping rope requires jumping. Unfortunately, when we jump in space, we're going to hit the ceiling every time. Here, Valery decides to abandon the jumping part of the jump rope and concentrate on the spinning part. This is not as easy as we expected either. Valery had to raise his legs without pushing off, then he has to swing the jump rope without hitting himself or the walls. An unnecessarily long rope gets tangled easily. Finally, it works. Valery makes several good turns of the rope, but he still tumbles and bounces into walls. Imagine you were jumping rope in space. What new techniques would you try?
So I hope you had some time to discuss some possible solutions on making the jump rope work. And maybe you even got the prediction correct. The biggest problem with trying to jump rope in space is the jumping part, because when we jump up, gravity doesn't pull us down. So that means when we go up, we're just going to keep going up until we crash into the ceiling. And just imagine if we were in a longer, taller space station, we would keep going up and up until we eventually came to the ceiling. Okay, so here's some possible solutions that I've heard over the years on how we could make the jump rope work. Okay, Probably the simplest and one of the most common answers is to push somehow, use a push force to come down. And I've heard everything from having the astronauts maneuver their body so that as they jump up, they would turn their body and their feet would be at the ceiling and they would push off with their feet. And they just keep doing this acrobatic move to where they're able to jump back and forth. I will say that would be a challenge, but technically it would work. Another push force that I've heard of includes having other astronauts at the top. So as you get towards the top, they would reach in there and push you back down so that you would be able to jump again. So those are some push force ideas on how we might be able to jump rope better inside of the space station. Another idea that I hear sometimes is to use magnets. One of the most common ideas, magnetic boots. And they've been everything from magnets that we're able to turn on and off with a button that might be inside of the handle. So we could activate the magnets as we clear the rope and it would pull us down. And then just keep going through that process where we turn the magnets on and off. Another type of solution that I've heard for this toy includes using the force of wind. So whether it's a vacuum pulling us down or a fan pushing us down, using wind as a force. And possibly my favorite idea was to have an astronaut with a helmet that had a giant spring on the top. So as you would jump up, your spring would push you off of the ceiling back down to the floor so you could jump again. And a similar idea I've heard to this one would be to have a trampoline at the ceiling that you would just crash into. So there are some solutions for the jump rope. The next toy that we're going to talk about is the boomerang. For this toy, we're going to ask that you pause the video now and talk amongst yourselves about what a boomerang does. What is it supposed to do? How does it work? Do you think it'll work inside of the space station? So pause the video, come back, watch the video, and then talk about solutions on how we can make it work. Here is the boomerang. Okay, hopefully some of your discussions with the boomerang included it's a toy that you use. When you throw it, it comes back. Okay, so the baseball is a toy you use, but when you throw the baseball doesn't come back, but the boomerang does. Is this because boomerangs like humans more? Of course not. No, there's science behind it. And if you really are confused as to why the boomerang comes back and the baseball doesn't, start with this question. What's different between the two? What is it that the boomerang has that the baseball does not? And your answer should eventually take you to wings. Now, the science behind the boomerang is pretty simple if we connect it to Newton's laws of motion. One of the rules says an object at rest will stay at rest, but an object in motion will stay at motion. And both of these things are true until a force acts upon it. So if we were to apply that logic to the boomerang, if we throw the boomerang in this direction, it's going to continue in this direction in motion until a force acts upon it. So we know the boomerang turns and comes back. So what's the force that causes the boomerang to turn? Well, the turning happens because of air friction force that occurs as the wings are spinning. In fact, if you throw the boomerang without having it spin, it doesn't come back. Or if you throw it the wrong way so the wings don't function the way they were designed, it doesn't come back. You actually have to throw it and spin it in the right direction. In fact, let me try to do this. I'm going to show this to the screen, and hopefully you're able to see the wings have a slight angle. And that means as they're spinning through the air, we have air friction. And because the wing is bent or curved, there is a different force on one side than there is the other. We would call this an unbalanced force. And in this case, as the wings are spinning through the air, it's pushing more on this side than it is this side, which means the boomerang is going to turn to the left. So when we throw the boomerang and have it spinning, it comes back to us because it's moving forward and turning left. So hopefully you now understand how a boomerang functions and why it comes back to you when we throw the boomerang on Earth. Now, the second part of your discussion probably involved, would it work inside the space station? And of all the toys that I've spoken about over the years, this question has been answered wrong more than any question ever. And most people do not believe the boomerang will work inside of the space station. And I always like to go back and look at the science of it. What would make it come back on the Earth? Well, we discussed that. It's wind friction or air friction. As the wind travels over the wings, it pushes it to the left. So if you're looking for a scientific explanation, just ask yourself, is there air inside of the space station? And the answer is yes. And so if there's air and the wings are spinning, will the boomerang turn and come back to the thrower? And as you saw in the video, of course, the answer is yes. So again, the boomerang, it's really kind of simple if you talk through the science of it. However, it is one of the toys that has a lot of wrong answers with it typically when we talk about it before we get into the science of what makes a boomerang work. Okay, now we are up to my favorite toy, and this is called the Kendama. Now, I enjoy this toy because it's a toy that involves hands-on engineering. Hopefully, you had a moment to make one or to experiment with one. We don't call this the Kendama. That's actually the Japanese name for it. In America, we probably call this the ball and cup toy. And that's exactly what it is. You throw the ball up and you try to catch it in a cup. And you can make your own ball and your own cup, and it's pretty easy. So the Kendama, or the ball and cup toy. So what I want you to do is to pause the video, take a moment to discuss how this toy works on Earth, discuss your predictions of what you think would happen, and then discuss how we could make it work better. I'll be back in a moment.
Kendama.
On Earth, gravity causes the ball to fall into a cup and to stay there, but not in space. Valeri tries to catch the ball in the cup and then on the spike at the end of the Kendama. In all attempts, the ball bounces away from the Kendama. Even pulling the Kendama down and having the ball move toward it does not result in the ball staying in the cup. Next, Valeri pulls the ball and the Kendama apart and releases them. Notice that the ball moves faster than the Kendama in both attempts. The ball is lighter, so it must move faster to conserve linear momentum. Also, the ball has less air resistance, but this is only a minor contributor to the speed difference. Watch as Valeri is finally successful in catching the ball in the cup. See if you can discover his secret before he shows you. Notice that catching the ball requires a very slow impact, even with the sticky tape that he put in the cup. This ancient Japanese toy requires modifications for microgravity.
Okay, with this toy, you probably had a moment at the end to see one possible way to make it work better. The astronauts put some tape in the bottom of a cup, causing the ball to stick in the cup. But the science behind the toy is kind of simple. You know, a lot of people, when they talk about their predictions, they sometimes forget that there's a string attached, and they say, well, the ball will just float there and it won't come down. Hopefully you've seen the video and you know that we can pull on the string and the tension will cause the ball to come towards the cup. The actual problem with using the kendama is keeping the ball in the cup, because gravity isn't pulling it down as the cup is falling around the Earth, just like the space station is. So the solutions are, how do we keep the ball in the cup? The crew put tape inside. There are a lot of other ideas that I've heard. But the bottom line is you could put anything sticky in the cup and it would work. So tape, glue, until it dries, as long as it's sticky, it would work. Sticky tack that we use to hang posters on the wall, that would work. You could even go to a supermarket and go up and down the aisles and come up with everything that's sticky, and you could put some of that in the cup and it would work. Maple syrup, ketchup, mustard, mayonnaise, all of that would cause the ball to stick in the cup. Other ideas that we've heard: build a lid. Use your hand as a lid. That would work. Magnets, making the cup and ball magnetic. That's another idea. Oh, Velcro. Listen to this. Velcro. Velcro is another idea that I sometimes hear. All of those are good ideas for making the kendama work in microgravity. Okay, so we've got one more toy left, and this toy is probably the most global of the toys, as everyone knows this as, well, everyone outside of America knows this as football, but we know it as soccer. And so what I'd like you to do is to talk about, for a moment, just pause the video, discuss, some of the rules of soccer, how soccer works, and your predictions. Then watch the video and come back and discuss some of the ways that you might be able to improve the game of soccer inside the space station. Have fun watching the crew play soccer in space.
We quickly discovered that the whole strategy for playing soccer must change when there's no force to hold our feet to the ground and keep our bodies from turning. Using feet to pass is always challenging, but even more so in space where we can't stay on the floor. But sometimes the aim is great, and it's time to duck if you're operating the camera. Notice how much harder it is to keep your hands out of the way in space. In space, we often use our arms to help position our bodies without touching anything. And watch how the angle of impact between the ball and the foot determines the speed and direction of the ball on Earth and in space. The astronauts are trying to kick with some force and not hold on to anything. It is much more difficult to give the ball speed with no surface to push against with your legs. Let's watch how Sergei and Valery play and think about how different it is to play soccer on Earth. Remember that hands are off limits, but your head is not. Soccer is an ancient game and a very popular one with people around the world. Now we know that astronauts can play it in the International Space Station as they orbit around the world as well.
Okay, so I hope you enjoyed that. It's really kind of, usually when I talk about soccer, it's the last toy. And most of the problems that you would have trying to play soccer in space are ones that we already experienced with other toys. So a lot of the solutions are the same. You could use some of the solutions that we use for the kendama, like you could put sticky tack all around the soccer ball, and it would stick to the wall, making it easier. So we could use previous ideas. There's one that I always like to bring up, and this is not an idea that's come up before, but one idea that we could use to make soccer work better is to have a larger ball. Yes, if we had a bigger target to kick, it would be easier. And so that's one possible solution. But I'm sure you guys had a lot of possible ideas on how we could make soccer work better in space. Okay, guys, that's our investigation. And if we go back to the beginning of the program, I hope you remembered one thing that we talked about is we wanted to introduce you to some careers. And as part of this lesson, you were able to be an engineer and solve problems. You were able to make predictions and set up experiments. So you were a scientist as well. So those are some careers that you were introduced to. And then another main focus of the overall investigation was to have fun. And I sure hope you did. I know watching the toys in space is kind of neat, but also the engineering part was fun and the science part about predicting what you think would happen and then seeing the results. So I hope you learned about careers, you learned a little bit about the science of microgravity, and you had fun doing this. That's the key. So thank you for your time. I hope to see you again in the future, and I hope to see you working at NASA down the road. Take care, everyone.